All right, so we were trying to look at a special case here, special case of Sylow's theorem. Perhaps it seems to be giving us trouble to think about whether the order of g equals p to the alpha times m. Why does that imply that order of h equals to p to the alpha? But maybe we can think of a special case. What if alpha equals to 1? What if we know that the order of g equals to p times m? Does that imply that the order of h equals to p, that there exists some subgroup h of g such that the order of h equals to p? Right. So far we've tried two strategies that are not really helping us. Finding an element of the group G, little g in G, and showing that it must have order P. So we've come out a little dry on what to do there. We've also come out dry on the idea that assume that by contradiction, suppose order of G equals P times M, and then let's assume that it's order of G equals P times M, but order of H does not equal to P for any H subgroup of G. And we saw that maybe that was also, it was unclear how to proceed. So this leads us to try something different. Okay, what if we try this instead? Suppose that the order of H does not equal to P. We're going to try and do the contrapositive here. So suppose that the order of H does not equal to P. Why does that imply that the order of G does not equal to P times M? Well, then suppose that for all subgroups H of G, order of H does not equal to P. Why does that imply that the order of G cannot equal to P times M? So let's try that. Let's try this. For all H in G, subgroup of G, we're saying that order of H does not equal to P. Okay? And we somehow from there want to conclude that order of G does not equal to P times M. So our key question becomes, how do we show that a group does not have a given order? Well, we have a couple of ways of showing that a group does not have a given order. One way is to show that its order is less than the given order. Maybe order of G is less than P times M. Or two, order of G is greater than P times M. Or three, perhaps, if order of G, okay, we've already done this before. It's still contradiction anyways, yeah. So maybe not that, but the idea would be if order of G equals to P to then P times M, then we have a contradiction. But didn't we just assume that if order of G equals to P times M, and the consequence is not true, that actually for all H, order of H does not equal to P? We saw that maybe that wasn't helping us, but it's still a strategy, but we're not sure if this is going to help us. How else can we show that the order of a group is not equal to a given value? Well, another way would be just to say, look, the order of the group does not even divide the value itself. Right? Because if the order of the group equals to that value, it better divide it, right? So, is there any other strategy we could use to show that the order of G cannot equal to P times M? Another long shot is to say the following, that G is not isomorphic G is not isomorphic to G is not or let's say G is isomorphic to a group. G is isomorphic to L, but order of L does not equal to P times M. Isn't that a possibility as well? Well, if you're confused about what it means to an isomorphism is, please yeah, please look up an isomorphism. What is an isomorphism? Right. Right. So this is a concept. Isomorphism. What's an isomorphism? So, is there any other strategy we could use to show that the order of G does not equal to P times M? Yeah, this seems to yeah, okay. So certain tactics we are not so sure are going to help us, like this one, that the order of G has to, let's put it in purple, that if the order of G were equal to P times M would have a contradiction. We tried this and we're not sure where it's going to take us. That the order of G is less than P times M. Well, the question is, well, how would we show that the order of G is less than P times M if we didn't know the elements that are in G? And the only information we seem to have here is that, look, for all subgroups, the order of the subgroup cannot equal to P. Okay. We're thinking of all non-identity subgroups once again, right? Actually, no, that's fine. For all subgroups H of G, order of H does not equal to P. Well, we said before, we could conclude from there that, okay, order of H actually, if order of H must divide the order of the group and order of H does not equal to P, can't we say that uh, order of H divides M? Okay, if order of H divides M for every subgroup, oh, maybe that's it. We're assuming that for all subgroups H of G, the order of H does not equal to P. Right. If that is true, and the order of H for every subgroup must divide P times M, right? The order of the group itself. Oh shit, we don't know that yet. Right, that's what we're trying to prove. Oh, maybe that's the idea. Well, let's see. Let's flesh this out. If it doesn't work, we'll maybe try some other strategy. But suppose that indeed for all H subgroup of G, order of H does not equal to P, right? And let's suppose that at the same time, we're going to use this contradiction strategy. Suppose at the same time, order of G actually equals to P, actually equals to P times M, okay? Then if order of H does not equal to P, aren't we saying that at the same time that for all H subgroup of G, okay, aren't we saying that then order of H has to divide, right? Every subgroup must divide the order of every subgroup divides the group, right? So if that is true, then aren't we saying that order of H must divide P times M? Okay, but if order of H does not divide P and order of H divides P times M, sorry, if order of H does not equal to P and P is a prime, right? And order of H, can order of H divide P then? Unless H equals to, the answer is unless H equals to the identity. So are we saying the following, that either H equals to the identity, or H, or order of H divides M. Could we conclude that? If we know that order of H does not equal to P, and order of H must divide P times M. Okay, if H equals to the identity, well, now we have two cases, right? So, well, one of the groups for sure is H equals to the identity, right? Isn't it? Like, the identity subgroup is really going to have this property. It's not gonna, its order is not going to equal to P, and its order is gonna, well, actually, does it even matter? Why are we using the either or? If H equals to the identity, doesn't the order of H still divide M? Okay. So, right. So, if either H equals to 1 or, so can we put it this way then? If order of H does not equal to P for all H subgroup of G, can't we say that the order of H must divide M, right? Because if H is the identity, sure. Well, doesn't the order of the identity divide M? Alright. Suppose H is not the identity group, is not the identity subgroup, and the order of H does not divide P, does not equal to P. Can the order of H ever divide P? Well, if order of H can't divide P, but order of H divides P times M, and order of H is not 1, doesn't that mean that order of H has to divide M? Okay. Well, if order of H divides M for all subgroups H of G, what are we saying here? Isn't the group itself, isn't the group a subgroup of itself? Right? Well, is the group a group? Yes. Is it a subset of itself? Yes. So isn't the group a subgroup of itself? Okay. If the group is a subgroup of itself, and we're saying that all subgroups, the order of all subgroups must divide M, and we're saying that the order of the group G must divide M, alright? But didn't we say that the order of the group was equal to P times M, right? So if P is a prime, right, can it be 1? Okay. So how can P times M, the order of the group, divide M? If we say the order of the group divides M, and we're saying that P times M divides M, right? But how is that possible? If P is some prime, isn't P times M greater than M? Okay. If P times M is greater than M, how can P times M ever divide M? Okay, so are we saying this is not true? Haven't we arrived at a contradiction here? If we have, aren't we saying then that these two statements can't be simultaneously true? That is, it is not the case that for all subgroups H of G, order of H does not equal to P. Okay. Let's not get ourselves confused here. We were trying to prove that if order of G equals to P times M, then there exists a subgroup H of G such that the order of H equals to P. So we decided to use a contrapositive tactic instead. Or we actually didn't even need contrapositive. The whole idea was, suppose order of G equals to P times M, and at the same time suppose that order of H does not equal to P for all H subgroup of G. If we can obtain a contradiction here, then aren't we saying that if order of G equals to P times M, that necessarily means that the order of H equals to P for some H subgroup of G, right? So the whole point was to assume order of G equals to P times M, and order of H does not equal to P for any H subgroup of G, and obtain a contradiction, right? Isn't that what we did? Suppose that there's a subgroup H of G, order of H does not equal to P, and order of G equals to P times M. Suppose these statements are simultaneously true. Can we obtain a contradiction? Well, if order of H does not equal to P for any H subgroup of G, aren't we saying that for all H subgroup of G, order of H must divide M? If order of H must divide M, aren't we saying that, look, in that case, since the group is a subgroup of itself, and we're saying that the order of G must divide M as well. But order of G is P times M. How can P times M right? How can p times m divide m, right? So haven't we obtained a contradiction? If we have, can we conclude the following? Right, please verify, perhaps we made an error. Can we conclude the following, that at least if order of g equals to p times m, that implies that the order of g, there must exist some h subgroup of g such that order of h equals to p. Can we at least conclude this much? Okay. So if we can, then wasn't this our base case? So maybe from here we can build and say, if order of g equals to p times m, if we are guaranteed this is true and when we have just p to the 1, can we maybe use this to prove that it's true for p to the alpha times m, that if order of g equals to p to the alpha times m, then there exists some h such that order of h equals to p to the alpha. That's one approach. Perhaps we can work now increase powers. And isn't another approach induction? Wasn't this the base case of our induction here? That, what is our base case? That if n equals to 1, that is if order of g equals to p times m, then order of h equals to p. Okay, so if we've proved the base case, doesn't that mean that our induction argument is now back in play? Perhaps we can show that if it's true for n, the result is also true for n plus 1. Alright, thank you very much for watching this video, and so we'll see in the next videos if this strategy pans out or not. But at least we've made some progress. We at least know that it's true for n equals to 1. Okay. Or so it appears. We'll have to cross-check that, make sure we didn't make any errors. And please do cross-check as well. Otherwise, thank you once again for listening, and have a relentless week. Bye. Thank you very much for watching, and have a relentless. Okay, bye. See you later.